Greetings, welcome to this new video about Thevenin's theorem. In this video, I will demonstrate the application of Thevenin's theorem through a step-by-step example explanation. By following along carefully, you will gain a clear understanding of how to apply Thevenin's theorem to solve practical problems. Let's dive in and begin with the solve the problem number 8. Let's consider this network consisting of 3 resistors labeled R1 through R3 as well as one independent source Vs. Additionally, we can observe the presence of a dependent source, especially a current-controlled current source. The question now is to find the Thevenin's equivalent with respect to terminals A and B. Let's move on to the solution. By applying the Thevenin theorem between terminals A and B, we can replace this circuit with a voltage source in series with a resistor, which will be denoted as VTH and RTH. I will start first with the determination of the Thevenin's resistance. This step can be done by removing all independent sources in the circuit, which means the voltage sources will be replaced by a short circuit and the current sources will be replaced by an open circuit. But we see the presence of the dependent source. However, the idea is to excite the network with the voltage VO connected between terminals A and B. We can set VO is equal to 1 volt to make the calculation easy. Our goal now is to find the current I/O through the terminals. Once we establish I/O, the RTH can be calculated by VO over I/O. To find the current I/O, I will apply the nodal analysis method. And I will consider I1 is the current through the resistor R1, I2 is the current through the resistor R3. By applying Kirchhoff's current law at node 1, we can write I1 plus 1.5 times Ix minus Ix is equal to 0. That means I1 plus 0.5 times Ix is equal to 0. Now, by applying Kirchhoff's current law at node 2, we can write I0 plus Ix minus I2 is equal to 0. And according to Ohm's law, I1 is equal to negative V1 over R1. And I2 is equal to V2 over R3. V1 and V2 are the node voltage respectively at node 1 and node 2. And we can see here that V2 is equal to VO. That means I2 is equal to VO over R3. And Ix is equal to V1 minus VO over R2. Now, by substituting A and C in 1, we can write negative V1 over R1 plus 0.5 times V1 minus VO over R2 is equal to 0. If we replace R1 and R2 with their numerical values and we continue simplifying this equation, we obtain negative V1 minus 5VO is equal to 0. And we know that VO is equal to 1 volt. That means V1 is equal to negative 5 volt. And now, by substituting B and C in 2, we can write I0 plus V1 minus V2 over R2 minus VO over R3 is equal to 0. And if we replace the resistors with their numerical values and we continue simplifying this equation, we obtain 12 times I0 minus 7 times VO minus 20 is equal to 0. And if we replace VO with its numerical value, we obtain I0 is equal to 27 over 12 amps. Now RTH is equal to VO over I0. And if we replace VO and I0 with their numerical values, we obtain RTH is equal to 444.44 milliohms. After finishing the determination of the Thevenin's resistance, we proceed to calculate the voltage, the Thevenin's voltage. The Thevenin's voltage is basically the open circuit voltage between terminals A and B. To find the open circuit voltage VOC, I will apply the nodal analysis method, and I will consider I1 is the current through the resistor R1, I2 is the current through the resistor R3. By applying Kirchhoff's current law at node 1, we can write I1 plus 1.5 Ix minus Ix is equal to 0. That means I1 plus 0.5 times Ix is equal to 0. And now by applying Kirchhoff's current law at node 2, we can write Ix minus I2 is equal to 0. The current flow in this direction is 0 because we have an open circuit. And according to Ohm's law, I1 is equal to Vs minus V1 over R1. And I2 is equal to V2 over R3 is equal to VOC over R3. And Ix is equal to V1 minus V2 over R2 is equal to V1 minus VOC over R2, where V1 and V2 are the node voltages at node 1 and 2. Now by substituting A and C in 1, we can write Vs minus V1 over R1 plus 0.5 times V1 minus VOC over R2 is equal to 0. And if we replace the voltage and the resistors with their numerical values and we continue simplifying this equation, we obtain 36 minus V1 minus 5 times VOC is equal to 0. And now by substituting B and C in 2, we can write V1 minus VOC over R2 minus VOC over R3 is equal to 0. If we continue simplifying this equation, we obtain 4 times V1 minus 7 times VOC is equal to 0. Now by performing 4 plus 4 times 3, we derive one equation in terms of VOC. And from here we can calculate VOC is equal to 144 over 27 is equal to 5.33 volt. VTH is equal to VOC. That means VTH is equal to 5.33 volt. After completing the calculations, I perform a simulation using SPICE to verify our results. Now let's proceed to the SPICE environment. Here is our networks drawn in SPICE simulator. This is the original circuit, and this is the Thevenin's equivalent circuit between terminals A and B. I connected a load, and I will call it R load, to both the original circuit and the equivalent Thevenin's circuit and simulate their behavior. Let's move on to analysis. This say analysis, calculate nodal voltages. We can see here that the voltage across the load resistor in the original circuit is equal to 3.69 volt, and the voltage across the load resistor in the Thevenin's equivalent circuit is equal to 3.69 volt. Upon simulation, we can observe that the two circuits have identical behavior when we connect a load between terminals A and B. This outcome confirms the validation of our calculation. Alright, thank you for watching this video. If you have any question, do not hesitate to contact me by email or leave a comment under this video and I will answer you as soon as possible. If you like this video, don't forget to subscribe and share. See you next time in another video about Thevenin's theorem. Take care and bye-bye.